I shall hit record, I shall share screen, and then the show is officially begun. Share the correct screen. That's always helpful, right? So you're not looking at yourselves. There we go. All right. So I wanted to start class the same way I started my other class, by a shameless promotion. Today's my birthday. I'm here teaching, doing what I love to do on my birthday. And I wanted to show you the present that I got this morning. So this is my merch. Jonathan made a t-shirt for me based on my channel. So here's the front that says Happy Garbage Day, which of course no one says but me, I'm pretty sure. And then the back, lisahoffman.com. So I have my own merch now, thanks to him. And I also wanted to show everybody the card that my son made me. He's in 2nd grade, he's 7. And his card is a theme of everyone in the family doing the things that mommy likes to do best. So here he is sleeping. Oh, here comes everybody. And here's me, here's watching TV, and their daddy's running. So he has a happy birthday to all of us. Oh, and I have more stuff. Thank you, everybody. I just got a balloon and food and a card. Oh, thank you, guys. It is a birthday. That's so nice. I don't even have to be shameless. You all just like spoiling me, so thank you. It's actually, no, I've got 4 minutes. 4 minutes. I was born at 2:07 in the afternoon, Central Time. So, yeah, birthday merch, birthday fun. And tonight I'm having Mexican and a blue margarita and cake. So it's going to be a fun afternoon. Yes. I know, there was, I will tell you, there was one previous birthday where I did go out to lunch for my birthday, had 2 margaritas, and then showed up to teach. I was extra funny that day, trust me. But in honor of, I am nothing but Mountain Dew in the system so far today. So we guys, now we have almost an equal number of roomers and Zoomers. So thank you, everybody, for being here and for the wishes. I have, let's see here, reminders. So homework 1 is due next Monday. If you don't yet know what you want to do with respect to the rest of the homeworks that involve individual data, please let me know. Be happy to chat with you. Your next formative assessment is the next thing after that, and then the thing after that will be practice with CFA, which we are going to start talking about handouts. For those of you who are in both classes, I want to point out that I'm going to have some crossover stuff across this section. So I'm going to have a little bit of like MLM stuff at the end of this SEM handout, and at the end of my MLM handout, I'm going to have some SEM stuff. So just like on TV shows where they like have the characters go on each other's shows so that you watch the one that you don't follow, they call it a crossover episode. I'm going to do a crossover episode in here. The other thing I wanted to make sure that everyone was aware of is at the end of all of my examples, so this is the example 4 we started last time, this is page 25, so quite a ways in, are lots of words. So at the end of all of my examples, I have a write-up as to how I would describe these analyses in a results section. So I don't want you, as we go through these examples, to feel like you have to like scribble everything that I'm saying down. It's here. Now these are more words than I would typically use, but this is sort of the longest version so that it is the most potentially informative and useful. But just so that you, as we're going through this, you don't get overwhelmed with the trying to take notes and listen to everything at the same time. We've got a description of all the stuff that's in this ginormous handout. So, all right. Questions or anything that we need to do before we dive back into the fun stuff?
Could you remind us when we should have data?
When you should have data.
So I know what I want
yes.
to use, and I also need to fill out some, like, please let me use the data forms.
The first assignment using data, your own data for analyses, I just looked this up, it's homework 3, and it won't be due until October 24th.
Right.
So you got a ways. Yes. Question?
Mm-hmm. So I have one research I really want to analyze. I'm asking for data right now, but I haven't got my response. So I don't know if I can get the response before Monday. I will still do it using that research article. But if I got refused for the data, could I change topics?
Yes. Yeah, if you need to change topics, you can. It's just that it's easiest if it's all one thing because it's meant to go together, but if that isn't going to work, then that's okay. Yeah, useful to you is the number one criterion for me. I want this to be something that you were going to do anyway, and you're getting class credit and feedback as part of your process. That's the objective. Okay, anything else? All right, then what we've been talking about in this class, make sure that I'm recording here because otherwise it didn't happen. There we go. Is model identification, and then just barely getting started with estimation stuff. So today we're talking about focusing on, in terms of the example, just this much. I think this will probably take all of class. Is I'm going to walk you through at least 3 of these 4 squares in terms of how you would set up the code to identify the model. And just to sort of big picture here, when I say identify the model or set up the model, scale the model, what am I talking about? What's the concern to be addressed? What is this for, this slide that I have in front of us?
This is like planting your flag, right?
Planting your flag? Yes, keep talking. Or make someone else talk, your call.
Model identification, is that related?
Okay, so she'd like to pass the answer. What is this for? Who wants to help her out? Your what? It's creating your, yeah, for what in particular? Scales of what? The factor, the imaginary thing. And that's why we have to give it a scale, is because it's imaginary. Excuse me, latent. Latent, unobserved, and imaginary. Those are all synonyms for our intents and purposes. So because the factor is imaginary, it has to have a mean and it has to have a variance. If you have more than one factor, you can ask the model to figure out what their covariance is, and it will do that for you. You don't have to worry about that part. So these are 4 choices for how to give our imaginary latent factor a scale. And there are 2 sides to the factor that have to have a scale, its mean and its variance. So with respect to the variance part, that's in the columns of slide 22 here. Your choices are fix the factor variance, usually to 1, or fix one of the item's factor loadings to 1. 1 is a convention, it's a convenience, but any constant will be fine. So long as you've planted your flag, chosen your key, you know, at the center of your formation, whatever analogy you want to use here, everything else will rearrange itself relative to that constant you've chosen to fix it at. And the logic of the second one here, the idea of giving a 1 to one of the factor loadings, what you are then allowing the model to do is to make the factor variance become the amount of that item's variance that is the good factor reliable part. So the amount of the item's variance that is supposed to be due to true score, that's what the factor variance becomes. So it depends on the scale of the item what that number is going to be. Otherwise, you can fix it to 1 and estimate all the loadings. On the other side, then across the rows of this diagram are options for what to do with the factor mean. And in almost every case on Earth, it's 0. You just fix it to 0 and you leave it alone. The alternative is to take one of your intercepts, probably the one that goes with your marker item here with whose loading is 1, and take the intercept and force it to be 0. And then what happens is the factor mean becomes the mean of that item. So any of these is fine. It's not going to change how the model fits. It's not going to change any of the conclusions you would draw. It just changes the scale. And this is the unstandardized version of the model, where the focus is on the recovery of the item means, item variances, and covariances. When we get to the standardized version, it will be exactly the same regardless of which combination you choose. The standardized version is all of the items have a variance of 1 and all the factors have a variance of 1 too. So you're working in like a z-score space essentially. Okay, I think that's all I wanted to say about that. The other part of model identification, how many items do you need to make your factor model estimable? 3. Is 3 good enough though? No, because what can't you do with only 3? Test it, see if you're right. Yep. If you have 3 items, then you have 0 degrees of freedom. There's a word for that? just identified. That means that you have spent as many parameters as you have pieces of information with which to estimate them. So you have basically just reconfigured your data. You haven't summarized or predicted it in any way. So you can have a factor that has 3 indicators, but you can't say, this is evidence that these 3 indicators measure one thing. You can't say that, because there's no other alternative. What if you only have 2? What's the term for that, other than broken, can't do it? Yeah. Yeah, under-identified, under-specified, yep. Not enough, can't do it. And the problem in that case is that you've got 1 covariance between the 2, but you're trying to estimate 2 loadings. So to solve the problem, what do? Set them equal, then we're back to 1. So in that situation, if you only have 2 indicators, functionally what you've done is take the correlation between them, draw a circle around it, and give it a name. That's what you've done. You have to assume that each item is equally related to that trait. There is no trait. It's literally just the correlation between the 2. What if I have 4? Then we're good. And what's the word for that? Over. Yeah, over-identified. Meaning I have degrees of freedom left over, and then I can test. Then I can see if I'm right. So if I have 4 indicators for 1 factor, I've got 2 degrees of freedom left over. Where it comes down to is I'm trading 6 covariances in the data are going to be approximated or recreated by 4 factor loadings. 6 minus 4 gives me 2 degrees of freedom left over. So there's room to be wrong. All right. If I have an under-identified model, can I just like add another intercept or something? Or can I fix it in any other way besides constrain the loadings?
Yeah, including more variables?
Including more variables, but if I only have the 2.
You don't have any DHS, do you?
I don't. Yeah, but in terms of where the problem is. So a lot of textbooks that I've seen focus on counting parameters, but that, I think, misses the point. Like, not all parameters are equal. Like, if you have an under-identified model, trying to add another intercept, like giving an item 2 intercepts, would never work. Trying to add another error variance would never work. The role of the intercepts is to recreate the item means. Every item has 1 intercept because every item has 1 mean. So that will never be a cause of under-identification. Likewise, every item comes into the analysis with a variance. And as long as we give each item a leftover variance, an error variance, not the factor variance, that number can become as big or small as it needs to perfectly recreate the total variance. So that's not the problem for identification. It boils down to the match between the number of loadings and the number of covariances every time. So as long as we have more covariances in the data than we have estimated loadings and factor covariances in models with more than 1 factor, we're good to go. Then we're over-identified, we can test, we can estimate. That was last time. All right. Any questions or things you want to review, talk about, elaborate? You look like you want to say something, so even with the mask on.
My brain, for whatever reason, has trouble counting covariances.
Mm-hmm.
Can you walk through that, right? So, like, obviously, I can see the error variances, I can see the factor loadings. Counting how many covariances for me, I always have this trouble.
So this little formula here is variances and covariances.
Okay.
To change it to covariances, it's V minus 1 instead.
Great. Cool formula.
Yeah, and then the plus V is for the number of means. Means and intercepts. Yep. So you may or may not see that. This is slide 23. Yep. Yep. Yeah, otherwise you just have to like visualize the matrix and sort of count them up in your head, which is just for the small cases I have it memorized. Like 2 items, there's 1 covariance. 3 items, there's 3. For 4, that becomes 6. For 5, it becomes 10. And after that, I have to do the math too.
So V times V minus 1 over 2, that's going to give you your covariance.
I believe that is correct.
Okay, thank you.
Someone who's better at math can figure that out and check that I'm right, but I believe that is correct. But I never trust my formulae recall off the top of my head.
I think that formula is for variance and covariance.
Yes, but to make it just covariances, I think if you do minus 1.
Yes.
That's right, we got confirmation? Yeah. And the data will always tell you too. So. Okay, shall we look at some data? Why not? True story, forgiving situations, a thing that I believe you can do. And the backstory to this, it's from a scale called the Heartland Forgiveness Scale that I was a graduate student at the time helping to do some of their psychometric stuff. And there are 6 items in this scale that measure forgiveness of self, 6 items that measure forgiveness of other people, and 6 items that measure forgiveness of situations, or what I refer to as the shit happens scale. Can you forgive something that is no one's fault and not have it ruin the rest of your life, basically? So their decision a priori with respect to wording was to deliberately try to balance across each of the subscales how many items had positive wording and how many items had negative wording. So in all 3 cases, there are 3 reverse-coded items and 3 positively worded items. We have some guests poking in. Okay, yeah, come on in. It's fine. It's cool. So this is a good decision from the perspective of not confounding valence and content. So what I mean by valence is like which way the wording goes and whether you need to recode. What I mean by content is what are these items supposed to measure. So as an alternative, how you might have screwed this up would be something like all of the items measuring forgiveness of others are reverse coded, and all of the items measuring forgiveness of situations are positively worded. Then the correlation between those traits is 2 things at least. It's the difference in how people process positive and negative words and the difference in forgiving others versus situations. That's what you don't want to do. There is an article that was just published that I plan to add to the reading list as to how to avoid this artificial dichotomy of whether it's positive or negative, and instead change the way you ask the question. So you can allow the answer choices to actually span negative into positive dimensions, and then you don't have to worry about reverse coding. But what ended up happening with these 6 items is the same thing that happens in a lot of cases. The items that measure the same thing in the same way, so that's shown by the red correlations here among the positive items, are more related, and items that measure the same thing in the same, those are the reverse-coded ones. These are the positively worded ones. They're more related to. So there is something that people are responding to about not just what the item is about, but how it is worded. Those are very salient features. I will show you later in the semester the ginormous structural model that I created to solve this problem. But that's not today. Today is just 6, much like you get to practice in your first homework. So we're going to do CFA, even though these aren't really continuous and they're not really normal either. And none of the fit statistics that we will get to eventually will tell us that this is a problem. But we will look at what does the factor model actually predict in terms of your predicted item response at each level of your trait, and are those predictions plausible or not? We will look at that eventually. So I think we started going through a little bit of M+ code to start with. So this is the front part of any M+ script, where you are explaining where your data is, what it's called, what information are in the data columns, and which variables are going to go into your model. So if your input file and your data file are in the same physical folder, you don't have to put the path in. You can just do this. But some of you may have to when you use the virtual desktop for reasons that I still don't understand. I'm just warning you. So in the example that's online of this handout, the original input files has an example of what that would look like, just in case it doesn't work for you. Free format is the default as opposed to fixed format, which is a lot harder to work with. and type equals individual means that we're analyzing individual item responses as opposed to a matrix. So one of the things I mentioned last time, you can actually input a correlation matrix as data and do a factor analysis on it, or a covariance matrix. You can do that. The names of the file, the variables that are in this file, and we're only using the 6 items that measure forgiveness of situations. In terms of naming things, because you are recreating your own new names for the use of this program, it doesn't know what they used to be called. Whenever possible, I try to use the same stem so that it would be like sit 1, sit 2, sit 3, sit 4, because then you can shortcut the list. You can do things like sit 1 dash sit 6, and it will understand that you mean all the ones in the middle. Now, me sticking an R on these ruins that. But I'm doing so to remind us which ones are reverse coded, because that turns out to be a very salient feature in what happens. If I forget this line, it's going to throw every single column into the model, even the ones that I didn't tell it what to do with, and that will cause problems. So don't forget your use variables. Also missing data codes. In M+, you are allowed to use just dots for missing data, and I do not recommend that. I've had problems that resulted from that. So it might be superstitious, but in my case, I do it every time. I fill in missing values with some giant number that's implausible. So you can do -99, you can do anything you want for this, but that way the program will recognize that as a value and not use it in the analysis. The ID variable option, then, if you output factor scores or any other piece of information that's individual specific, this will keep the ID part of that file so that you can merge it back into your original data. Type equals general is there's a few different types of models you can run. This is the one that I think we'll be doing all semester. Estimator tells it what kind of way of finding the answers you want. This is regular flavor maximum likelihood with a robustness correction to it. MLR is what it is called. If your data are somewhat deviated from multivariate normality, it tries to figure out how far off it is and use that as the basis for correcting fit statistics and standard errors of all the parameters. And I didn't really understand this very well until I read chapter 5 of Craig Ender's book, which is on your reading list. So for those of you who want to know a little bit more background as to how this works, he makes it very readable. So even though it's a book about missing data, his explanation of maximum likelihood, I think, is very, very good. And just regular maximum likelihood and how it works. That's something we'll talk more about probably next week, not probably today. But he has the, sort of the more technical details, including showing how maximum likelihood reduces to the sums of squares stuff. It's a simplified case. So I felt like that was instructive, but anywho. I think that's all we had talked about last time, is that right? So ready to move on? Look at this. So we haven't talked about some of this stuff yet, but there are extra pieces of output, as you can tell from the command that I'm asking. The one that we will look at today is this one right here. It's asking for the standardized solution. So asking for the results of the model in a correlation metric, which is scale independent and useful for evaluating which items are relatively more related to the trait, because it puts them all onto that same z-score metric. Extra pieces that I'm not using yet, but that we may eventually use when we get to our last model, you can ask it to output a predicted factor score for each person. So it is a prediction, it's not the actual one, but it's useful for making pictures and other kinds of descriptive types of statistics, and you can make all kinds of pictures in here as well. Okay, so here's our code then. I've got M+ first, and then I've got R Levon second for the first model here. So every model that we're going to work with in this handout has this as a starting point model. So you'll see separate files. Let me see if I can open it real quick so I can show you what it looks like inside the download packet. I've got M+. Let me see. Can I open it in a browser so that it will blow up? No, it won't. I can open it in this one, though. All right. So the way that I have this handout is Like all the models, like here's one set of models, here's all the models, but there's exclamation points in front of every single line. That's how you turn it into a comment, and that's how you can have all the models in one file as opposed to separate files. So there's one input file that has everything that we're going to go through, and then separate output files that have each results of each model. So model is the command that says, okay, what would you like me to do with your data? And then you tell it. Okay. So what I would like to do to start with is test the idea that these 6 items measure one thing. That's what they're supposed to do. Let's see if I'm right. So anything in green is a comment. So I've tried to write out, in all cases, what the following command is doing. So you would read this as what the line below is actually accomplishing is described up above. So these are the factor loadings. The first thing that I have to do is create a name for my imaginary variable. A good name for this factor would be called like situation forgiveness, right? That would be a nice name. Can I type situation forgiveness in M+? No, why not? Character limit, 8 characters or fewer. Yep, it's 1985 up in here. They're focusing all their effort on the machinery and not the input and the output. So 8 characters. So sit is the name of my factor. In Stata, by the way, anyone who's trying to do SEM in Stata, you have to have a capital letter as part of your latent variable in Stata. It's the one time you get capitals. I know it is. It's dumb. But I tend to write in title case anyway. M+ output is all uppercase. It doesn't care. It just spits it back at you. So the name of my factor is sit. This is entirely your choice, what you call it. I would recommend using a name that you know what it means. By is the announcement, hey, I'd like to tell you now which items measure this latent factor. And then I list them out. So right here. And then every command ends in a semicolon in M+. So that is the command terminator. The stars in M+ indicate a parameter that is to be freely estimated. So what that star refers to behind sit1r is the factor loading to be estimated for how the situation factor predicts the item 1 response. That's what it's referring to. You do not have to type the stars for all of the items, only the first one. The way that I write out my code for these packages is so that it is completely transparent what is happening and you don't have to memorize what a default is. But I will show you down below here the quicker version in just a second. So I am asking for all 6 items to have their factor loadings estimated. The only way that I can do that is if I am willing to identify the factor by fixing its variance to a constant instead. So the fact that I've chosen to estimate 6 loadings means that I also have to choose to fix the factor variance. So the corresponding sit at 1 down here, whenever you list the name of a variable by itself, what you are referring to is either its variance, if it is a predictor, or its residual variance, if it is an outcome of something. It knows which it is based on the context of everything else that's in your code. So the @ sign in M+ means fix it at 1. Don't find it, make it 1. So far my model is identified on the variance side because my situation latent factor has a variance of 1. That allows me to estimate all 6 loadings and let them be whatever they want. Okay, with me so far?
Yes.
Hit me.
My only question is, would there be an instance, I'm assuming it's the different boxes you were talking about.
Yep.
Where you would fix one of those 6 to 1?
Yep, the box we are in right now is this one, top left.
Great.
Yep, that's where we're at. This is what I prefer, because then the factor is interpreted as a z-score, and I know what a 1 unit change means. It means a standard deviation. Yep, thank you for the question. I have that in words here, but top box on the left is a little shorter.
And then if you, like, you would just set 1, there's no instance, at least right now,
Yeah.
I'm
Yeah. In 2 weeks.
Right.
That's coming. Yes. But just having all 6 be estimated means they each get to be whatever they want. No constraints yet. Yes. Foreshadowing. So this line and this line go together, essentially. Things in brackets, moving down to the next part. When you list the name of a variable in a bracket, you are either referring to its intercept, if it is an outcome, which these item responses are, or you are referring to its mean, if the variable is a predictor. So I am asking it to estimate all 6 intercepts, 1 per item as well. And the corresponding identification constraint that goes with that is down here. Because I am estimating all 6 intercepts, the only way that my factor mean will be identified is to fix it to something, and 0 is my choice. I don't have to type that, but again, I'm writing everything so that it's completely transparent what is happening. So all 6 intercepts, factor mean is fixed to 0. All 6 loadings, factor variance is fixed to 1. Now, what if you switch these around? What if I said factor mean is 1 and its variance is 0? What would happen?
I should fix the intercept factor load, the factor loading of the first item.
No. Good guess, though. What will happen? It will break. Because I just told it that my imaginary variable is a constant. So this is an easy thing to screw up, which is why I'm making a point of it. Because you look at this code and be like, what's the difference? No. The variable outside the brackets is a variance. Inside the bracket is a mean or an intercept. So yes, has to be this way. Last but not least, the error variances. So again, just listing the name of a variable by itself is referring to either its error variance if it is an outcome, or its variance if it is a predictor and it knows which is which. Okay. So how many different parameters have I asked the model to estimate? We'll count them up. How many loadings? 6. How many intercepts? How many residual variances? 6. So yeah, an easy math. Every variable, every outcome variable has 3 things. Intercept, loading, error variance. So I know right off the bat I got 6 items, that's 18 parameters. The other methods of identification don't change that math, because I would swap 1 loading for 1 variance. The net result in terms of the number of parameters is the same, or I would swap 1 intercept with a factor mean. So unless you're setting up some kind of model that is a stricter version with constraints, it's 3 times the number of outcomes is how many parameters you're estimating. Now the people who made M+, the mutanes, don't like typing. So one of the things that you will see in their examples is the bare minimum code. In reality, all you have to type is this. You do have to tell it to free the first loading, because by default it fixes it to 1. And if you want to free the first loading, you do have to tell it to fix the variance of the factor to 1, because otherwise it estimates that. You do not have to type the stars on anything but the first one. You do not have to refer to the intercepts because they're automatically estimated if a variable is an outcome. You do not have to refer to the error variances because they are automatically estimated if the variable is an outcome. So this little code down here does the exact same thing as the longer code. The longer code is more transparent. Okay, how are we doing? Reasonably okay? Yeah? It's not so bad. So here are some output then from M+ first. So unstandardized model results, factor loadings, sit by, and then it lists all of these. Let me blow this up a little bit. So yeah, everything's in uppercase. So whatever case you write in, it don't care. It's just going to convert it to uppercase. The columns that we're looking at, the only way that you can tell what kind of parameter it is by the section headers for the rows, because every column is the same regardless of what kind of parameter you have. The first column is the parameter estimate. Its most likely value given your data set. Then our friend here, what do you think SE stands for? Standard error. What is a standard error? We'll do a little review of basic stat here. What's a standard error? Yeah, the standard deviation of the sampling distribution. Yeah. This is the average offness of the parameter in any one sample relative to its population value. It's an index of inconsistency, where bigger is badder. Estimate over standard error, what do we usually call that thing? Yeah, that's our test statistic. Now, there's a column here that's missing that we would normally see for denominator degrees of freedom somewhere in the output. So if I don't have that, which I don't, what test statistic is this being treated as? T or Z? This is Z. Yep. So that's one of the issues with SEM software more generally, is that there are no degrees of freedom for the denominator being used. So that means what you get out of here is going to be some kind of Z, or in the case of multiple things at once, it's a chi-square. Z squared is chi-square, just like T squared is F. So these are Z's and chi-squares. And last but not least, two-tailed p-value, the usual interpretation. It's not 0, it's 0 to 3 decimal places. And yes, there is a way to request greater precision on the output, but it's a giant pain in the ass because it's unformatted and it's in the order of the parameters with no labels whatsoever. Seriously. I know. I'm just the messenger, though. It's not my fault. So what are we looking at here? These are factor loadings. These are slopes. These describe how related each of these item responses is to the factor predictor. So if I were to put them into a sentence, for instance, 1.234, and I didn't make that up, that's just what it is. It sounds like a number I would have made up. So 1.234 is the change in what per what? And Zoomers, I'm watching the chat if you want to play along. 1.234 is what in a sentence?
A change of the factor loading of 1 results in a 1.234 change in SIP 1 R.
Yeah, this is the change in Y for a 1 unit change in X, just like every other slope you've ever seen in your life. The question is, what's X and what's Y? X is the factor. Yeah, it's a factor loading slope. So as the factor increases by 1 unit, and this is where we got to know the scale of our imaginary variable, right? What's a unit? Well, it's a standard deviation. So the difference between somebody who has a factor score of 0 and somebody who has a factor score of 1, the difference in their expected item response to item 1 is 1.234. And it goes the other way too. If I go down the factor scale, then their expected response would be lower by 1.2 if they have a standard deviation under the mean of 0. Factor loadings are almost always going to be significant. You can just basically ignore the rest of these columns here. It's a pretty low bar to ask if your item has anything at all to do with the factor, right? Because the null hypothesis of 0 means your item completely sucks. That's a pretty low bar to cross. So we don't worry about significance, we worry about effect size. Speaking of effect size, is 1.2 good? It's bigger than 0. Is that a lot? It's the same problem as any unstandardized slope. In order to know what 1.2 means, I have to know the scale of the variable. I know that each of these items is measured on a 1 to 7 scale. So it's like changing like a whole response option per standard deviation. But no, these aren't effect sizes. I'll have those on the next page. How about situation item 2? Yes, and you got the right answer in the chat for that one. Same thing, right? As factor score increases by 1, the expected response to item 2 goes up by 0.7. Now, just staring at these numbers, is 0.7 less than 1.2? Staring at the numbers? Yes, it is. Can I say that item 2 isn't as good? Yeah. It's scale dependent. So it's on the same scale in theory in terms of a 1 to 7 response scale, but I don't know how much variability is in item 2. So we have to resist the urge to look at these numbers and draw conclusions relative to each other about these items, because these are unstandardized and scale dependent. Yes, sir.
I see the loadings are kind of oscillating.
Mm-hmm.
It's like 1.7, 1.7.
Yes, you do see that.
Is that because we specified the model a certain way, or is it just like a coincidence or something in the data?
It's something in the data. What looks like it's happening, and again, we can't say that for sure because these are not on the same total scale, is that it looks like the reverse coded items are weighting heavier in defining the factors, what it looks like. So the factor looks to be more not unforgiveness, whatever the hell that is. Exactly. But all of these at least have some loading that's bigger than 0. But no, I did not do that. The data did that. Moving on, the next thing it will give you is means and intercepts. And the difference again, conditionality. A mean is for variables that are predictors. An intercept is for variables that are outcomes. And you'll see that the mean of the situation latent factor is 0 with a standard error of 0 and a test statistic of 9999. That's not a number. Okay? 999 is m plus going, whatever, it's fixed. So they're not real. And it's fixed because I literally said, make it 0. I fixed it. It's not allowed to get found. It's not allowed to be anything else. And the only reason that I had to do that is so that I could estimate all of these intercepts. So an intercept, back in basic stat, what's an intercept? What's an intercept?
The conditional mean of the, okay.
Expected value when your predictors are 0.
That one? Yep, conditional mean when?
When the factors are 0.
When the factors are 0, which are our predictors. Yep. And series helping me. I would say conditional mean and intercept are synonyms. Mean is marginal. So, and what did you say? Y when x equals 0. Yep, all of those things are correct. See, I'm not trying to, I'm trying to be like, no, you know this, right? It's all the same things you already know. It's just that we're talking about an imaginary x as a predictor. So because we set the model up so that the factor mean is 0, these intercepts are indeed the item means. That will not be true unless the factor mean is 0, though. So I will keep calling them intercepts because they are conditional. These are the expected item responses for somebody who has an average level of forgiveness. And they're on a 1 to 7 scale. So the average response is a little bit on the high side, reflecting the fact that these data are negatively skewed. Question?
Related to IRT, is this the difficulty in doing it?
It is a difficulty parameter, but it's easiness in terms of the direction. Yeah, because the higher the intercept, the easier it is to get a high score at a low value of the trait. Yeah, it's easier to endorse. So,
Number we are talking IRT for negative 4.5.
yes, well, this is not in logits.
Oh, yeah.
There's no link function happening here. This is just straight 1 to 7. We're going to pretend like that's normal and continuous. So this is, this means that for somebody with an average level of the trait, they're halfway between whatever 4 means and 5 means. That's where they're expected to be. So we are going to use these intercepts and these loadings, and we're going to draw regression lines. And we'll figure out at what point does the model predict an expected response that goes out of bounds. Because as theta gets higher, right, it's 4.5 for a 0 person. We add 1.2 to that for a positive 1, another 1.2 for up to 2 standard deviations. We're going to hit the ceiling pretty quick. So that's one of the things to evaluate in terms of whether or not this model is reasonable, is how quickly does it predict scores that you can't have on your outcome. Okay. Same thing here. The variance of situation factor forgiveness is 1, because that's what I told it to do. And then these are the residual variances. So are these error variances, residual variances, specific variances, or unique variances? Yes. The answer is yes. These are not the factor. I don't care which word you pick. I'm going to stick with error variance because residual variance is a different, residual is used in a different way. But of course, M+ labels them as residual variances. But this is the amount of the total variability in each item that has nothing to do with the factor, that is unique to that item, which is where the term comes from. And of course, these are all going to be significant too because they're not perfect indicators. So if I were to take some of these values, for instance, for item 1 and write out the model, this is what the factor model tells me. It has an intercept of 4.5, a factor loading of 1.2, and I can use this equation to get a predicted y given any value of x. That part is a little more straightforward. Now, in terms of what's happening under the hood, remember the whole goal of this process is to try to find item intercepts that best recreate the means, item error variances that best recreate the variances, and the big one, loadings that recreate the covariances. We're trying to match the pattern in the data. So we've got, let me go back to, let's go picture. We'll go picture, then we'll do equations. So the model says that the relationship, say, between items 1 and 2 is item 1's loading times the variance of the factor times item 2's loading. That's what the relationship between these two is supposed to be, any item on the same factor. In terms of matrices, this is the slide that I added words to so I could get the letters right. The end goal is to try to recreate the overall pattern of variance and covariance for these items. That thing is called sigma. It does so with loadings, factor variances and covariances, and then error is tacked on to the end. So in our example, I can write out how the model recreates the total variance of item 1 like this. It is the item 1's loading squared times the variance of the factor plus the error variance. So the amount of variance that is due to factor is that much. The amount of variance that's due to error is that much. And that gets us back to the total variance that is actually in that item. So it's roughly half and half, it looks like. Can someone do the math real quick? What's 3.049 minus 1.526? That's less than 3. Thank you. That's where I'm at. Like half and half. No, for real. Can someone give me the number? How much? 1.523. Okay, remember that number. It's going to show up again in the output in like 5 minutes. Okay, 1.523. Thank you. In terms of the predicted covariance between items 1 and 2, it's loading of the first item times variance of the factor that's supposed to be in common times loading of the second. What the model is saying is that the only reason that these two items are related to each other is because of their contribution from the factor, and that's it. That's what it's saying. So if we put the math in, the model says their predicted covariance is this number right here, 0.86. Okay, that's what the model says. However, in the data, the covariance between item 1 and item 2 is only 0.577. So we call that wrong. Eventually, where we're headed is literally summing up like all of these offnesses for every element to try and figure out how badly or well our model fits, where closer is better fitting. If I have 6 items, though, is this model over-identified, just identified, or under-identified? Over, meaning I have degrees of freedom left over, meaning I could be wrong. So I'm off by 0.3. Looks like I could be wrong. Okay, how are we doing?
I feel like you could be wrong and you would know it.
You would know it. Yeah, I do know it, because I stared at the correlation matrix at the first page, and I know I'm wrong.
Right.
But we're going
I'm
through
saying,
this.
like, you could be wrong in other instances,
Yeah.
you just wouldn't know it.
Mhm. Step 1 is always stare at a correlation matrix, seriously, because like whatever's going to happen is foreshadowed right there. Question? Where did that come from? The data said. Yep. So I outputted a covariance matrix like in any package. So covariance meaning the scaled version of the relationship. That corresponds to a correlation of 0.2 between those two items. Their covariance is scale dependent. So item 2 has less variance in it than item 1, even though they're both on a 1 to 7 scale. So that's why I say they're not quite on the same scale. Now, wouldn't it be nicer if like I could just talk about correlations since we like know how much that is? Wouldn't that be nice? Yeah? Nikki's the only one who thinks it would be nice. Anyone else think it would be nice if we could just talk about correlations, because then I know what those numbers mean? Let's just talk about correlations by looking at the standardized output. So I'm on page 4. So STDYX means fully standardized with respect to X and Y, meaning now we're going to pretend that our item responses are z-scores, mean 0, variance 1, and we're going to pretend that our factor is also a z-score, which it already was, but it would fix it if it weren't. And now everything on this page is standardized. So the factor loadings are no longer...
Quick question.
Yeah, go ahead.
This, when you run the code that you walked us through, it outputs both the unstandardized and standardized together?
It
Or are you running
does.
different code?
It does, because this option on output.
Great.
Yep. And I have that like at the front of the file, so I always get that. There is also a choice in our Levon where we're going to go next that has standardized that you can ask for too. Yep. Yep. So where are we? Okay, here we go. Standardized. So these are slopes, but they're standardized slopes. And given that each outcome, each item response outcome is only predicted by one predictor, these are Pearson correlations. So how correlated is item 1 with the trait that it's supposed to measure? 0.7. I know what to do with that number. That's pretty good. It's not super great, but it's not bad. How correlated is item 2? 0.5. How correlated is item 3? 0.78. How about item 4? So the oscillating pattern you noticed earlier, still here. Now, I'm not going to do any significance tests, but I'm just going to eyeball this and say, yeah, item 1 is loading more highly than item 2. It looks like item 3 is also loading more highly. 5 is a little bit higher than the others, but kind of crappy, and the worst item is number 2 in terms of what they have in common. That's what this model is telling me. I still get standard errors for the standardized things, test statistics, and p-values. Usually the p-values will agree, but not necessarily. The mean of the factor is always 0 in the standardized solution. The variance of the factor will always be 1 in the standardized solution. And residual variances, these are the proportion of variance not explained. And R square is the last one. that is literally the square of the loading. So just like if you have a regression model that has one predictor in it, and the correlation between the predictor and the outcome is R, and you square it and you get the model R squared, same thing. Because I have one predictor per outcome in this. So item 1 is like literally half and half. So 0.707 squared is 0.500. That's where that came from. So these are our effect sizes. It's up to you whether you want to talk about effect size in an R-square metric. If I did that, I would talk about what proportion of the total item variance is due to my situation factor. Half of it, you know, a quarter of it, 60% of it, etc. Or I can think of effect sizes in a correlation metric of R instead of R squared. 6 of one, half dozen of the other. So this is a lot easier to interpret in terms of making comparisons across items, which ones are the best, according to the model. Okay. Does that make sense? Reasonably so? So then in terms of recreating stuff, the job of the standardized solution is to recreate the pattern of item correlations. Rules are the same. Loading times variance of the factor times loading. So the predicted correlation between items 1 and 2 is the standardized loading for item 1 times the standardized factor variance, that will always be 1, times the standardized loading for item 2, which works out to be a correlation of 0.3. The actual correlation between these items from the data is only 0.24. So the model is over-predicting how related they're supposed to be. Same conclusion, regardless of whether we're looking at the unstandardized solution or the standardized solution. Yes, indeed. Okay, how are we doing? That's not bad, right? Question?
Is it, I guess, like a hard cut for early predictions? So say the model predicted 0.245. You know, like, is that still, it's black and white?
It is not black and white. Where we are eventually is going to sort of tally up all of these offnesses and figure out as a whole how close the model is to the data. And we have a test statistic that tells us how far away the model is from the data. And we make a black and white thumbs up or thumbs down whether that test statistic is significant. But in terms of like just knowing that the model doesn't fit doesn't help you fix it. Like, oh, it's broken. What's wrong with it? I don't know, but it's broken. Like, that's unsatisfying. Looking at each of these gives you a clue as to how it's broken. Like, well, it overpredicted these relationships, but it underpredicted those. Maybe that points towards 2 factors, or maybe that points towards some other way of setting this up that would better match the data. So yes, not a hard and fast rule for each one, but more is worse in terms of being off, being wrong. Okay. R users, here's your section. So the syntax that goes into Lavon all looks like comments. That's what it looks like in RStudio unless you change it somehow. But basically what happens is that you write out your entire model within a set of quote marks, and then that is an object that you feed into the Lavon function. That's how the SEM packages work. So we're using Lavon in this case. I called my name of my model syntax syntax 1 because it's my first model. And the comments are the ones that start with this symbol, which is either a hashtag if you're young like you guys, or a pound sign if you're old like me. And the code itself is every other line in here. So the translation from M+ to Lavon is actually fairly straightforward. To set up the name of a factor, it's equal squiggle, and you add the items together that you want to be indicators, which actually is terrible because you're not adding items together at any point in this. The items are the outcomes, and this makes it look like they're predictors. But it's just the context of the program. Intercepts are requested with squiggle and then a 1. So I've got 1 for each item in here. Error variances is double squiggle. 1 for all 6 of those. And then variances of the factor, double squiggle, where I have a 1 and a star because it is the opposite of M+. Stars are fixed in Lavon. Stars are free in M+. So 1 star sit means make the situation factor variance 1, and sit with a single squiggle is referring to its mean, which I'm saying make it 0. So all of the loadings are going to get estimated, all of the intercepts are going to get estimated, all the error variances are going to get estimated, but I have fixed the mean and variance of the factor to 0 and 1 respectively. So within the Lavon package, there's a Lavon function, there's a CFA function, there's an SEM function, and there's probably others that I don't even know of yet. From what I understand, each of them has built-in defaults that make it easier to write the code. So I'm showing you the Lavon version because it's the most transparent and the most complete. Like, this is what you're asking for in the model. But if you're like, screw that, I don't want to type that much, then this is all you need. 1 line. So I have a separate object that's syntax short because there are options that you can choose as to how you identify the model. So either way, if I use the Lavon function, the arguments are what syntax do you want, what data do you want, what estimator do you want, and then you can invoke a bunch of other default settings with respect to convergence and stuff as to what package you want it to look the most like, which is M+. And then STDLV means standardize my latent variables, make their mean 0 and their variance 1. So you don't even have to write that either. Did you have a question?
Does this article work just as well as M+?
Yes. For this model. For CFA models, yes. There's only a few things I've found where it's not providing the exact same information.
So for the rest of the course, there will be occasions where we must use M+.
In the IRT section, yes. Because full information, maximum likelihood with IRT is not in Lavon. It's only in other places. People used R 2 years ago when I first brought this course to Iowa, and they were okay with the homework system, making it work. So that's one of the things that now that I know how to do it, I can check and make sure that the answers work both ways. But yes, I hate R with a passion, but Lavon is like the first thing I haven't hate. It actually works like it's supposed to. It's very lovely. So the Lavon call then, and then the summary function, you can ask for pieces of output to be turned on and turned off. And fit measures is one. We haven't talked about what those mean yet. R square equals true and standardize equals true. That's your standardized solution. So if you turn those things on, then you get the standardized solution. The same is true for the shorter version of the syntax. So all you really have to write is just which items go with the factor, because you can tell it to use, here it is, the standardized latent variables. And one thing that's nice about the Lavon output is that, here's what it looks like. It puts both solutions onto the same page. So there's not 2 separate sets of output that you have to scroll through. It has 2 different standardized solutions at the end. You want the last column. That's standardized. So latent variables, here's my factor loadings, which you would know because it's labeled as equal squiggle. Here's a pro tip, by the way. Don't ever make a table for a manuscript where the label is equal squiggle. Do not expect your readers to know what the hell that means. Okay, that's just bad. Like, I don't know why we couldn't just write out latent, factor loadings or something, but equal squiggle is not helpful for the rest of the world. Am I right? Yeah, that's one of my pet peeves is when people make tables where they have like the Greek letters as the only identifier for the row or something. Like, really? Like, I don't remember what beta is now or delta or what are the other letters are. Like, can't you just use some words? So yeah. you are allowed to take this output and copy it and make tables out of it, but we need some better labels. But otherwise, it's the same. Estimate, standard error, labeled explicitly as a z-value, and then two-tailed p-value, and then the two standardized columns. So we have the factor loadings first, the intercepts and means. So this is one difference in how the output is presented. It doesn't separate what's a mean from what's an intercept. It's all just intercept. So the mean of the situation factor being 0 is right there. And note that it has blank spaces right here. Remember why that would be? Why don't I have a standard error or a test statistic on my factor mean? Is what? Because it's constant, because I set it to 0. So that's where m plus does 999. This just makes it blank. So, and then the variances, which you would have to know contextual. The dot, I think, means residual variance, and undot means regular variance, I think. At least that's what it seems to be. Okay. So we would come to the same conclusion with respect to all the parameters to 3 decimal places to be able to do this. Yep. So stdyx is the last column here. And the output looks exactly the same, whether you make a longer call to Levon that writes everything out, or the shorter call that just specifies the factor loadings. All right, how are we doing? Now, we don't know yet if this model's any good. We have a hint that it's probably not good based on how far off even just one of the covariances was that's predicted, but we don't know yet. What we do know is that it looks like all 6 items are measuring this common factor to some extent. They do have something in common. What I also don't know yet, and what we won't know from any of these analyses with just these items, is whether the thing that they have in common is actually situation forgiveness. I named it that. I think that's what it's supposed to be. But all these results are telling us is whether there is something in common, right? We don't know what that is. Trying to demonstrate that it is, in fact, forgiveness of situations, which is different than forgiveness of others, which is different than just rumination, which is different than just being depressed, that's a validity argument. And we would need to bring in external data and other pieces of information to bear on that argument. So just keep that in mind as you're setting these things up. Like, what you name it, like, that's up to you. We could be wrong about that. But we're trying to make an argument based on the content of the items as to what they're measuring in common. The math will back us up as to whether there's something in common, but not what that something is. So the variance that these items have in common, I draw a circle around and I name it situation forgiveness. That's what we've done. I've taken all the covariance across items that they have in common and drawn a circle around it. Okay, other questions? Yes?
Please feel free to answer this in broad strokes, because I
Okay.
imagine we're going to get into it.
Likely.
So I'm assuming the fit measures are going to speak to like all of kind of the offness that you were talking about.
Yep.
When we get like how much offness that we have, do we then go back and try and figure out like which items are the most off kind of a thing?
Yep.
Like, okay, cool.
Yep, that's exactly it. Let me foreshadow. There is a spreadsheet that goes with this set of models. And yes, you can do all of this in R or other packages, but I like spreadsheets because they show the computations. So in particular, the first tab here on the spreadsheet that goes with this example, I've labeled single factor models. And I have in Excel, let me see if I can make it big enough to show you all, the original item covariance matrix. So this is just from the data, straight up. The model predicted matrix, which I have up here in the formula bar where it comes from. So I did the work to show you like how each of the model predictions would happen from this as a function of the loadings and the factor variance. And then what we're going to end up looking at is this last matrix here, which is literally the difference. what it was minus what it was supposed to be and how far off. So here's the sum total, foreshadowing what's going to happen, of how our model matches the data or not. You'll notice the diagonal, where the variances are, is pretty much perfect. It's rounding error. And that's because each item has an error variance that will just soak up to become whatever it needs to be to perfectly recreate the item variances. What's not in here, but also for the same exact idea, the means are perfect because each item has an intercept. It's all of these covariances that are off to some degree. And it's exactly what you said. It's like, well, 2 and 4 want to be more together than the model says, but 1 and 4 want to be less together. And it's that pattern that is indicative of how the model is not working. And then you can revise it. So that's where some people would say the line becomes blurry of what is confirmatory versus exploratory, because we're kind of messing around in an exploratory way to fix it. But the framework that we have that provides us with this information is useful. So ideally, like if you're wrong, you would go out and get a new sample and see if the thing you came up with holds that time. And every time you have to mess with your factor structure based on the data, you'd want to replicate it to make sure it wasn't just that sample being idiosyncratic, but that your results would hold more generally.
And when you say a second sample, it's not a second sample like in a longitudinal sense where it's the same people?
No, different people.
Okay.
Different people from the same population, ideally. Because if you're like, well, this scale worked on college students, I'm going to go to the nursing home and get some old people, you might end up with a different answer for that reason, because it's not the same people, and that's an invariance problem. So yes, to the extent that we have to change our mind as to what the factor structure is, that merits replication, always. So, but this is what's going to happen. We're going to distill this down into, okay, how well did we do, and how can we make it better? That's coming next week. Because it's 3:14, and that means it's time to go. So, any questions before I go have the rest of my birthday? We're good? All right, well, it is not garbage day. That means I say have a great weekend. Let me know if you need anything, and I will look forward to seeing your homework assignments on Monday. Bye for now. Bye.